Hello and welcome everyone to our monthly WFO webinar. My name is Ilya Karnaukhov and I'm the Senior Business Development Manager at World Forum Offshore Wind, or shortly WFO. Today's webinar is on offshore wind technological updates, and it's my great pleasure to welcome our two excellent speakers for today. We have Judith Bosch, a Technical Business Development Manager at Avient company, and Olli, a Naval Architect at Solis Marine Engineering. And before we jump into their presentations, let me tell you a few things about WFO. The organization was founded in 2018, and we're a nonprofit entity focused exclusively on offshore wind, and we promote it worldwide. Our members represent the complete offshore wind value chain, and we have international setup with offices in Hamburg, New York, Taipei, and Tokyo. And in terms of our activities, it's very straightforward, as we focus on three things only. We provide advisory services for offshore wind around the world. We inform about offshore wind. We are publishing periodical reports, facilitating various working groups and such. And we organize events for connecting the global offshore wind community, such as this webinar, but we also have workshops, special webinars, and physical events. And in terms of our members, at the moment we have over 110 global members from around the world, and they represent the entire segment value supply chain from North America, Europe, Central Asia, Middle East, and even Australia. If somehow you're still not a member of WFO, please feel free to check our website and also contact our Managing Director, Gunnar Herzig, for any questions or requests you may have. And now, just a couple of words about the structure of this webinar, which is very simple. During the first part of this webinar, we have two presenters, and you can submit your questions on the hand right side, and submit your questions through the chat function. And then during the second part of the webinar, we have a Q&A session where those questions would be addressed to our speakers today. And that's about it from me. Without any further ado, Judith, the floor is yours.
Okay, yeah, thank you, Ilya, for the introduction. Today I'm going to talk about Dyneema. As you maybe some of you know about Dyneema, we were formerly owned by DSM, but now Avient is our mother company, and is also the producer of the Dyneema fiber. Yeah, today I will be talking about what Dyneema can do in offshore wind, and I think it is obvious why offshore wind is an important market for us. As you can see in the picture, it is a market which is a growing market. This is, by the way, a picture that comes from the DNV Offshore Energy Report. And you see that it is a growing market, and partially that will be in offshore fixed bottom wind, but partially also in floating wind. And the challenge for both markets is, of course, to lower the cost in euro per megawatt hour. And the target is in 2030 to be below 50 euro per megawatt hour. With our offerings, we want to help to achieve this challenge of lowering the levelized cost of energy, and that we want to do in two ways: by offering our lightweight products, but also by offering developers and users in the value chain our engineering tools that we have developed in order to exploit really the full potential of Dyneema and to reduce over-design, which is currently still often the case. Before I go into the case studies that I prepared for you, I would like to tell you a bit about our product, Dyneema. Dyneema is actually the brand name for ultra-high molecular weight polyethylene. And maybe most of you know polyethylene from the plastic bags or the shampoo bottles. But the difference with Dyneema as we produce is that it has very long molecules, and by our production process we make sure that these are nicely aligned, and that gives it incredible strength. The combination of strength with lightweight, brings the advantages of our products. For example, in steel ropes, we have for the same diameter, the same strength, but we are 7 to 8 times lighter. We even float on water. Next to that, it has a good abrasion resistance, high durability, cut resistance, resistance against deformation, so a high modulus that makes it very suitable for ballistic applications, but also a certain level of fatigue resistance. Now, that makes it suitable for a number of applications. And yeah, I will explain in the next slides, what are these type of applications. As you can see from this slide, we have really a diverse range of applications. I will not go into the detail of all the applications. I will just highlight a few to give you a flavor of the different application fields where we are active in. And the first one is, for example, you see it here in the corner, is personal protection. Where Dyneema protects people in the army from getting shot. And against bullet, it is not only the helmet and body armor, but also vehicle protection. And the main advantage is that we are 40% lighter compared to armats, which is the next best alternative. And of course, you can imagine that often in the harsh conditions, this 40% weight difference makes a difference if you have to carry your gear all day long. Another example that I want to highlight is in the top, it's aquaculture. This is a market that is a growing market. Fish farming is going more and more to offshore regions where you have more predators and the sea is rougher. And the advantage is that you can make relatively thin nets, fulfilling all the requirements that are needed. But also due to the thin netting structure, the water flow, the natural water flow through the water is better, which makes the fish grow faster, which is of course the aim of fish farming. Now, then a third example that I want to highlight is in the sailing industry. It's in the middle, and most people know ropes with Dyneema from that. There our ingredient brand is well known. And then we're talking about applications like the Volvo Ocean Race, although it is not called the Volvo Ocean Race anymore. It's now the Ocean Race or the Vendée Globe, where you can use ropes of Dyneema to maneuver your sails. And because of the high stiffness, so the low stretch, it has a direct response on the sails, and therefore, you can get maximum performance from your sails. As I said, I prepared some of the case studies, and here is an example that you see in the background of what we do. We want to offer not only products, but also engineering tools. And some of us are a bit confused because I think we are a rope manufacturer. We are not a rope manufacturer, but we do produce some ropes, but that is only for testing purposes because we break them in our tech centers. Well-known rope manufacturers are, for example, BBRG, Lankos, Gleistein, Bexco, and then Fibermax for tendons. But if you want to see the full list, you can see it on our website. Our strategy for offshore wind is to be really a true partner for the industry. We want to cooperate to lower the levelized cost of energy with minimum risk, of course, and through solid engineering practices. And to do so, we have intensive cooperation with installation companies and system designers in projects. Now, as you can imagine, some of these projects are covered by confidentiality, but luckily some of these are not or not anymore, and those studies I can share to you. These are the ones that I've listed for lifting slings, lifting chains. That is mainly for fixed bottom. And then number 3, 4, and 5 is more for floating wind. And then as a dessert, I still want to say something about bio-based Dyneema. I directly jump into the first case study, and that concerns the Walney extension project, which was performed by SAL, who needed to load 87 monopiles for transfer. As an often used alternative to steel, polyester slings are often used, but in this case, these would become too bulky. What was used for this project, what you see in the pictures, are slings made by Gleitstein, one of our licensee customers. Their Dyna 1 rope was made with Dyneema SK78 fiber. And this has only 1/5 of the weight of a polyester and half the diameter. So it was much easier to pull the slings around the monopiles to put it on the right position, which really reduced the loading and unloading time. And that was 1 hour for one monopile, but in the total projects that saved them 3.5 days. Now, besides the lower weight, also another advantage is the low elongation, and that makes positioning possible. So, of course, this is one of the examples, but there are many more, but I won't bother you with all of them. But basically, it comes down to several advantages that these slings are offering. They are strong and lightweight, making them faster for lifting operation. But on the other hand, they are also soft slings. So that makes that there's no damage to the load, no extra protection needed between the sling and the load, unless you, of course, would like to protect the sling itself. But Dyneema also has a good durability, so it has a proven reliability and safety, so making them also suitable to use them for multiple projects. And that is also the reason why that slings are used since 2010 for many different wind projects, not only to lift monopiles, but also blades, turbine jackets, and transition pieces, and also to position substations. We noticed that often there is a lot of questions about also legislation and the do's and don'ts. It goes in too much detail now, but we also offer trainings to end users who still have questions on this. So if you're interested, let me know. Then the next case study is one of my favorites because I've been twice to Nordenham in steel wind to witness the advantages of using Dyneema. One time it was really focused on the lifting slings, a similar example as the previous case study. But the second time it concerned the synthetic chains with Dyneema. And on this picture, you see Bobby. Bobby is a Filipino, one of the crew members of the Jumbo ship. I think it was a fair player. And he spoke really good English, and that was very nice because I could have a talk with him. On this picture, he is carrying actually 2 × 6 meters of 16 tons capacity lashing chain, which is weighing less than 10 kilograms. In steel, this would weigh almost 80 kilograms. So you can imagine that then to transport those synthetic chains towards the location where you need towards the lashing point, you would actually need a forklift truck. Maybe this form factor is not yet known to you. That it could also be because it's only introduced in 2015, and before that time only chains were available for metal. And of course, the advantage of a chain versus a steel wire rope is the length flexibility. You can put the hook into each link. But of course, the disadvantage is the weight, and that has been taken by Dyneema as a positive challenge to invent something, and that is what we did. This chain also has a special Möbius twist, which has been patented. But as I said in the beginning, we are not a rope supplier. We also are not a chain supplier. So we license out that technology to our customers. And currently we have 3 licensees offering those chains into the market. That is from Base to Leipzig and Murtra. And they market those chains. In this case, Jumbo was approached already several years ago, and they had a project which was called the Easy Lash project, which took them 2 years to evaluate the performance of these chains. And And the conclusion of the experiments were obvious. They managed to reduce at least 50% in lashing time, so that saves time from the crew members, and they can already start doing something else, and that of course saves also harbor time. One of the main concerns that they had was about the lifetime performance. So that is why the experiment also lasted for 2 years, where they used them intensively. Of course, it comes with the usual manuals about the do's and don'ts, but they were very satisfied on the performance and the durability. Also, lighter, safer, easier usage compared to steel, so crew members were less fatigued at the end of the day. And actually, Bobby mentioned very enthusiastically to me that when he was moving on the deck with his chains, he said it is such a great innovation. It's the best innovation in lashing for the last decades. And I think most of these crew members are normally quite critical on new developments, but this really brought them a benefit. On the other hand, also the soft touch, same as with the slings, no pain damage, and also less injuries for the crew. Jumbo was one of the first, but in the meantime, also Seaway Heavy Lift, Herema, and other big shipping companies have introduced these chains for lashing capacity. These were the examples that I had for the fixed bottom. I now would like to go a bit into the floating. One of the first examples is with principal power. Here, the example of the wind float Atlantic, but also the Kinkerdine. Where principal power used in the top part, as you can see in this picture, ropes with Dyneema DM20 from Langhorst. And then the bottom part was more the classic catenary. But they took a holistic view. They wanted to lower an installation cost, they wanted to lower the investment cost, and to improve on the performance. And in the next slide, I will explain to you how this multiple angle cost optimization works like. So for the fabrication, often Dyneema, people think that Dyneema is very expensive. However, from the material point of view and cost per meter, it is similar to chain, but 15 times, but that is 15 times heavier, or sheeted wire ropes, which is 7 times heavier. From the installation point of view, the rope is compact. It has the same diameter as steel, while polyethylene or polyamide would give a more bigger diameter rope. There is fast connection possible because of the lightweight, and the prelay is possible on the seabed. Due to the buoyancy, it forms a natural arch in the water, so it can be easily tension again. And the good thing is the learning from the first project wind float was that actually the pre-tensioning doesn't make any sense. So for the Kinkerdine project, ABS waived the need for pre-tensioning, which of course also reduces the need for really big vessels to do this pre-tensioning. So you remove one of the installation steps. Then concerning operation and maintenance benefits, of course, as you can imagine, if you have a steel chain, it has a quite vertical angle towards the platform. With Dyneema, it is more under an angle, and that increases the platform stability. Furthermore, of course, for these kind of projects, 25 years of lifetime is required, and we were able to manage that with Dyneema DM20 grade, and that is also verified by ABS and DNV. Next to that, it's no steel, so also it doesn't have any, doesn't need corrosion maintenance. One of the topics, of course, to take care of is the marine growth. It has the rope has a cover preventing fouling to get into the rope, but of course the rope can get more heavy due to marine growth. Although all of this, compared to all of the other synthetic materials, this is the lowest with Dyneema, which is also proven by aquaculture applications. And it can be easily removed. So for the projects that are now, there is regular check on fouling. Then the next case that I want to highlight, because the previous one, the principal power, of course, for a demonstrator project is nice, and you can have this catenary, but if you want to install hundreds of these wind turbines, it becomes more critical. Also, the footprint to the seabed. So that is why Glossen, for example, developed this TLP design. In this case, they have floater with 5 connection points, which connects the floater to the seabed. And of course, you can imagine that, there will always be length differences, either by the manufacturing of those tendons or by unequal design or seabed. So this normally requires that you use subsea tensioners. These are quite expensive. Dyneema is a viscoelastic material, so it has certain properties. I will not go into the details. Tomorrow I have a session as well in the WFO for the mooring subcommittee, where I go a bit more into the details. But due to this viscoelastic behavior, the difference in loads or difference in lengths can be leveled out. And in some of the cases, it's possible to do without subsea tensioners, and that is, of course, again, cost advantage. Now, then for this, Glossen Pallister has chosen parallel wound tendons from Fibermax, which are different than ropes. And in ropes, you have a braiding angle, so the position of your Dyneema fiber is not longitudinal. And in this parallel wound tendon, actually the Dyneema is wound parallel around the thimble, which gives a very high strength efficiency and good stiffness. Actually, unfortunately, the project of Glossen that we were working on was financed by the Energy Transition Technology Institute, a UK private partnership. And this project was stopped because the intended site in the UK Wave Hub was last minute not allowed to install such a tall turbine. However, Glossen is still active, and with their Pallister design is one of the 9 winners of the Floating Offshore Wind Readiness Prize, which is a US prize to promote floating wind energy platforms technology. So we expect that new opportunities will rise from that. We are also working with more TLP designers, because we have developed this special model for making more accurate mooring and to reduce on over design. And this in that time also we received an endorsement of qualification plan by DNV. The next case that I would like to highlight is with Saipem, and this is a project which a prototype has been installed in Naples, and the Saipem has is a design which has a counterweight with 6 tendons attached to it, and then of course next to that you still have also the mooring lines. But the focus that I would like to have is on this keel lines, we call it, and then I go a bit further into the details. This was a project in Naples, and we had the opportunity. In this case, you see that it's hanging on a big crane, and you see this it's difficult to see, but you see 6 tendons here, and of course also that is again an overdetermined systems. But on the top of these systems, we had these tensioners in order to to compensate for length differences, but we used it the other way around. We wanted to check our model for load sharing capability, and we on purpose induced a length difference in order to see how good our models were matching with the practice. So we made sure that some of the tendons were 2 of the tendons were shorter, so they received all the load. And you can see from this, From this picture, the moment they started, the delta between the highest and the lowest load was about 900 kilograms. But after 40 minutes, less than 40 minutes, this was already reduced to 650 kilograms. And yeah, the good thing is that we talked to Saipan, and they said it is for us important that it levels out within the first moment. So with this model, you can see that the dots are the lines are the experiments, the dots are the predictions, that our model is very capable to predict that behavior. So for their future projects, they rely on these kind of models from us, and that could prevent using subsea tensioners in the future.
Judith, like 5 minutes?
Yes, okay, I will manage. Thank you. This is maybe a very busy picture, but it shows that besides the mooring lines which I addressed and the key lines which I addressed, there are other possibilities still. Langkos was used for the ropes in the Kinkerdijn project, and for the Stiesdal project, which I did not highlight it here, but that is also a keel design. Their Dyneema ropes were used for both the lowering and lifting lines and the key lines. But here you see a new idea, and that is this small chains that were used for lashing. We understood from one of the projects that an anchor needed to be dropped 3 times in order to have the good position to hit the bullseye. And that, of course, and it costs a lot of time and money. So the idea was that you attach towards the rope. Here a small example. You can make a direct link between the rope and the chain. And in this case, this chain is a 600 tons chain. In order to make sure that if the anchor positioning is not correct, you add a component which is a mega chain, which is produced by Moorlink. This is only now a prototype. We are in the process, however, to qualify this for use in offshore applications. Another idea that we have, and that is mainly with our customer Samson, is to use also the rope in the bottom as a bottom part. And this rope has a special feature where all of the different strands are covered with a Dyneema cover. And this has been actually used in one of the projects, not for floating wind, but which gives very good results. And then, of course, here we have the parallel wound tendons that I also addressed with the Pallister concept. Now, the last slide that I have is about biobees. We talk about Dyneema. Dyneema is normally used from naphtha, which is a fraction of crude oil. However, we have on our agenda a very strong sustainability roadmap. And one of the topics is that we want to be less reliant on fossil resources. So it is now also possible, and we already sell it, to make Dyneema bio-based, and that is based on a mass balance approach, where we use a waste product from the pulp and timber industry, which is a residue product, and make it like a bio naphtha that can be used to produce Dyneema, and that gives enormous savings in carbon footprint. So yeah, to wrap up this presentation, we have a 10-year track record in offshore wind. Mainly used is our grades SK78 for slings and DM20 for moorings. Yeah, we are really dedicated to work together with designers and people in the value chain to lower this levelized cost of energy. That we do not only by offering our products, but also our models. Yeah, and we seek really to extend this cooperations with installers. So if you are one and you are interested, reach out to me. My contact details are on the next slide. And thank you for your attention.
Excellent. Thank you very much, Judith, for this very comprehensive overview of cables and mooring lines for offshore wind. And now It's my great pleasure to introduce our next speaker, Olli Short. Olli, over to you.
Oh, thanks very much for the opportunity to present here, and thank Judith for that presentation. I'm going to talk about something fairly different in this slide, but hopefully it's still of interest. So as I said, I'm Oliver Short from Solis Marine Engineering. We're an engineering consultancy service, and we specialise primarily in renewable energies, but also clean shipping. I think we see the future of both of these technologies as quite important, and are very much combined, these sectors, to allow us to meet the 2050 clean maritime targets of net zero. So today I'm going to talk through a little bit a few clean shipping projects that we have undertaken and are ongoing at the moment, and then talk a little bit about a study into potential fuel demands for to power the clean shipping industry, and how offshore wind might supply these in the form of e-fuels. So just a quick introduction to who we are. So we're a small team based in the southwest of England in the UK. So we're a mixture of naval architects and master mariners. And then we also have a team in Singapore, which again is a mixture of master mariners and naval architects, which sort of service the Asian market. But this time I'm going to talk about more about UK and more about the southwest, because that's where we're sort of located, and with the potential for the floating offshore wind in the Celtic Sea. So yeah, here's just a sort of an overview of sort of what we do as a company. So in the renewable energy sector, we've been involved in both sort of fixed and floating wind. In the last decade, my boss primarily has been involved in various tidal projects around the UK. And then we've also sort of touched on various different wave projects. We're also quite interested in hybrid, primarily combining sort of wind and wave to get the maximum output from different platforms and increase capacity factors. And in the clean shipping sector, we've done various projects looking at different fuel types to get a better understanding of different fuels. So these sort of involve various electric projects, hydrogen, ammonia, methanol, and also hybrid combinations of both. So I'm going to talk to you through a few different sort of clean shipping projects that we've been undertaking, and then we can talk through about how these sort of might be powered by floating offshore wind in a study sort of based on the southwest. So one of the first sort of fuels is just full electric. So we've done sort of various different designs. We've done 150 sort of pax passenger ferry. This is what we're operating in Plymouth. Well, it was a design in which we got to, so a preliminary design submitted to BV. Unfortunately, the cost of electric, especially batteries, is quite high, so we're still waiting investment for that to go forward into an actual sort of workable product. We've also done some work with sort of RS Electric, which is quite interesting because they actually understand that the sort of electric vessels have to be operated slightly different due to their limited range. So their sort of new design, they're sort of pushing a different way of operating it as well. And we've also done some sort of novel propulsion for these electric vessels. Sort of looking at more hybrid fuel technologies. So through Innovate UK grants with various different project partners, we're involved in two. So H2 Transship, that was looking at an electric hydrogen conversion of a survey vessel. So ripping out all its prime movers and replacing with fuel cells and batteries and compressed hydrogen. And then also a CHAMP project, which is a much smaller vessel. And this was a methanol electric hybrid, sort of trying to get the benefits of both methanol and electric to increase the range and capability of these vessels. And then finally, the last few. So we're also working on the MMA Levique. So this is an ammonia fuel conversion project. So we're going through full DNV fuel-ready approval, and this will hopefully be operating this year on ammonia. And then finally, another one which we're just starting is a full hydrogen conversion of the same vessel as we actually said before. So this is actually putting the hydrogen systems in and actually getting it operate in the next 24 months, hopefully. So in these various projects we've done sort of various understandings of the different technologies, and a lot of these, especially sort of electric, is more sort of catered to short-term shipping, sort of domestic and fishing, due to the limited range of these fuels. However, sort of the deep sea shipping consumes a much greater proportion of the diesel and is contributing much more emissions. So there's various different options of fuel for these vessels. So we're talking sort of LNG biofuels, but primarily I'm going to talk to you about ammonia and potentially hydrogen. So these two fuels, their sources, you can get sort of blue from sort of carbon capture, bio, but the one we sort of want to talk about today is electric. So this is sort of a zero carbon alternative, looking at e-ammonia or e-hydrogen, which can potentially come from the offshore wind sector. So a study that we did just to understand sort of the bunkering requirements and fuel requirements in the southwest. This is primarily because we're based in the southwest, but also catering for the sort of Celtic Sea development, and just understanding sort of ports in the southwest which might supply the offshore, floating offshore wind sector. So whether this is sort of platform supply vessels, survey vessels, crew transfer vessels, but then also looking at the potential shipping routes, so sort of north, south and east, west transits off Land's End, which a huge amount of shipping goes through to go up the English Channel, to looking at potentially bunkering fuels sort of offshore or from these floating offshore wind platforms, and just trying to get an understanding of the potential sort of requirement for fuels in this area. So what we did, we used some open source AIS data. This was provided by the UK MMO. And they provide sort of heat maps around the UK, as you can see in this image, of various different AIS datas. And these are broken down into sort of categories, AIS categories 1 to 10, which I'll touch on the next slide. But this is sort of a very high level study. So we've got no sort of departure destination speed, vessel particulars, drafts. So it is sort of quite a high level study at this stage, but hopefully it gives a bit of an insight into the potential fuel requirements in these areas. So once we've got our ports designated, and we've also got our AIS vessel categories, we can then sort of start looking at the demand or the potential vessels in these different ports. So you can see here, this is how we're defining the different vessel categories from 0 to 10. And then the plots that you can see here, hopefully it's just about large enough for you to read. So these different vessel categories down the bottom and these different locations that we've sort of marked. So you can see in sort of the bigger ports in Plymouth, you're seeing a lot more sort of port service craft, but then down the bottom in these sort of land end, north, south, east, west transits, you're seeing much more passenger cargo tankers, which are obviously going to have much higher fuel demands. So once we've got the vessels, we understand sort of the amount of vessels in these different areas and in our ports, then we have to try and convert this into a fuel requirement, sort of a bunkering requirement. So to do this, we've taken each vessel from the AIS data, so vessels sort of 0 to 10, and we've defined a base vessel, which is sort of the average for each category, which gives us a fuel requirement for those different categories. Obviously, the vessels are going to be operated differently, so a tanker is going to have be operated much more than, say, sort of a personal watercraft. So that's also reflected. And then sort of looking at the installed power, we've just sort of given an average fuel burn of about 175 per kilowatt hour. And then we can convert this for each of these different vessel categories into a requirement for diesel, hydrogen and ammonia. So if we look at the hydrogen and ammonia, so we know the requirement for each vessel, and then trying to relate this into offshore wind. So potentially how big an offshore wind farm would you need to supply these vessels? We've worked this the whole way through. So if we had offshore wind creating electricity, you then actually get to create hydrogen, you have to run that through electrolysis, which is an efficiency of around 70%. And then to go through to ammonia, you're looking at sort of the Haber process, which also has an efficiency sort of loss on that one. We also had to factor in sort of the wind farm capacity factors. I think on the UK average the last 12 months is about 42%, but on these offshore floating sites, it might be quite a fair bit more, sort of up to the 50–60%. But at the moment, I think we just assumed a conservative estimate. So from this 1 ton of diesel, we've worked out we need about approximately sort of 26 megawatt hours of wind equivalent to supply this. So if we actually look at a case study of what this actually means, so if we just take these two, the Land's End north-south transit and the east-west, you can see the AIS to vessel category plot in this corner. So we're looking at primarily tankers and much bigger vessels, and this is vessels transiting in those areas in a week's period. And then using our sort of base data for these different categories, we've estimated that as a diesel fuel burn of about 68,000 tons, and then an equivalent ammonia to power these vessels of about 137,000 tons. And if we were equating that, so all these vessels were purely powered from wind farms, so e-fuels, that's looking at sort of 23 gigawatts of power to service all these vessels. So there's a huge requirement in the future to clean up the shipping industry and fuel these international sort of shipping fleets. If we look at sort of the DNV forecasts and trends related to this, so you can see ammonia, sort of a carbon neutral fuel at the bottom there. You can see that their predicted trends by 2050 really increasing. So I think these fuels, methanol and ammonia, and hydrogen are going to have a substantial increase in the next sort of decade or two in usage and be more common in smaller vessels and also larger vessels. So there's a few considerations for these fuelings of these different technologies. So improving fuel supplies, so how in different ports and harbours going to do this, whether you can do offshore e-fuel sort of bunkering for these different tankers that are passing through, especially in different offshore wind sites, which are a long way offshore compared to sort of fixed. There's also sort of improvements on the vessel design side, so making these vessels just as sufficient as possible to just minimise their power requirements. And there's also potential risks in these categories, sort of the safety of these new technologies and integrated supply chains. But we understand also that not sort of one single fuel is appropriate for all vessels. So different sort of availabilities of fuels and also different operating profiles might prefer different fuel types. So the last thing I'm going to talk about today is just one last project that we're working on actually at the moment, which is another Innovate UK project, which is looking at a new design for a survey vessel, but this could be transferred over to various different vessels servicing the floating offshore wind industry. And this is trying to be a bit more fuel agnostic, so it'll have a full electric propulsion and powertrain, and then it will sort of be more plug-in, so you could just put a full battery bank in, you could do hydrogen with fuel cells, it could have ammonia running to a generator. So it's trying to be a bit more modular with your systems so that you can cater your vessels to the different profiles or operating regions that it's operating in. I hope that was a nice overview of sort of what we do in a few projects and a few thoughts. My details are on the screen if you want any more information about any of them. But thanks very much for listening.
Okay, great. Thank you very much, Olli, for this wonderful and very in detail presentation about offshore wind updates and fuel and ships, and that's great. So now we have 15 minutes or so for the Q&A session, and the first question would be rather general to both of you. What are the current and most pressing technological challenges in the offshore wind industry? And let's talk about like specifically and cable and lines for Judith and fuel and ships for Olli. So maybe Judith, we start with you. And once again, the question is, what are the, based on everything what you discussed and shared with us, what are the main challenges to overcome in the next few years?
Yeah, I think one of the topics that I addressed is the over-design. And I think especially now with the first demonstrators Everybody wants to be secure, doesn't want to run into a risk. But in order to make it economically viable, it's important, to trim down. And I think, what I presented is that there are opportunities. There is experience also in getting these new technologies proven by certification via DMV, Bureau Veritas, ABS, and so on. That is the big challenge. And then the next thing is to scale up.
Okay, great, thank you. Olli?
I think one of the biggest challenges is, which we hear a lot sort of in the Southwest development, is sort of the ports and harbours infrastructure that's going to cater for these services, but also the vessels. So how these potentially new vessels, which are going to be sort of clean for this new clean industry, are going to operate, and also then like sort of portside facilities and fuel storage for bunkering these different vessels, I think is a big challenge and opportunity in the future.
Okay, sounds good, thank you. So the next question is regarding how much progress has been made to enable making cable lines and part of the ships maybe from the recyclable materials. So what's the current status for the recyclability of the parts of the industries you work in? So maybe we start with Olli and then Judith.
Sorry, can you repeat that question? So talking about...
Yes, how much progress has been made to enable making the cables and mooring lines in terms of Judith's case, and in your case, Olli, in your industry, what's the trend in making parts of everything that's been used recyclable?
So I'll change that slightly. So in terms of recyclable, so there's I'm not sure about fully sort of recycling these bits, but I think the refit option is sort of a way to move forward and sort of create less waste. But that has its challenges, especially in the sort of the shipping industry of meeting these different regulations for these new vessels. So I think there's also a potential for new builds requirement, and then that would involve recycling of vessels, but it's not something I'm too aware of, I'm afraid.
Okay, thank you. Judith?
Yeah, thank you for the question. The first step is that we made was going to bio-based, so less dependent on fossil. That doesn't make it yet recyclable. What we see is we are a fiber supplier. Our customers make ropes, and it helps a lot for the recyclability if it doesn't consist of multiple different materials. That makes recycling more difficult. So we are also looking into the development of coatings which have a similar properties as a Dyneema, so the design for recyclability. On the other hand, we have started up a circularity team, because we realized we are at the beginning of the value chain. We are a fiber manufacturer, then you have the rope and the end users, but we have set up this circularity team in order to provide answers to that. It's not only by finding a technical solution, but also making sure that the materials are logistically gathered and returned. And one of the options that we are looking into mainly now is chemical recycling, which means that we bring it back again to a component which is like a naphtha, to bring it again into the process and to make new Dyneema out of that. So that also the properties of the end product is guaranteed the same. This is a process where we expect at the end of this year we have the first results. So by the time floating offshore wind that these come out, the mooring lines come out of the water, that is in 25 years time, there should be an answer ready. Especially the industry that I mentioned in the beginning, in aquaculture, there is already a demand to do that much faster. So before 2025, we want to have a technical solution as well.
Okay, thank you very much. Next question is, based on your experience and understanding, which role, let's say, artificial intelligence and other approaches to really make everything, like intelligent systems, could play in the further development in the offshore wind industry? So maybe if you can share your thoughts, Judith, first, and then Olli, that would be great.
Maybe you give it first to Olli. I need to think about it.
Okay.
Yeah, I'll have a crack at first. So I think it's sort of two bits of this. I think in the sort of design space, I think the role of the engineer or the naval architect will change slightly. Will be sort of a more setting and bounding parameters and letting sort of AI and technology come up with these novel and clever solutions that we might not be able to iterate through fast enough. So I think AI has a huge potential there as sort of a design tool, but then also sort of real-time monitoring and adapting to optimize systems. I think when it's deployed in offshore, looking at sort of mooring tensions, but also increasing like capacity factors from varying different parameters. I think it has a huge potential there as well. So I think it's going to play a massive role in the industry going forward.
Okay, great, thank you.
Yeah, and for me, I see that a lot in our industry. I mean, a lot of ropes, and they are made with machinery, but there's still a big part that is handmade. That is the end connection. But on the other hand, I see some potential for artificial intelligence, mainly by monitoring on the failure mechanisms. I see that there are some things can happen, especially maybe you've seen that there is a big crane from McGregor now out with a synthetic rope to an offshore crane. And there, the inspection of the rope and the number of times it goes over sheaves and bending, I can imagine that artificial intelligence there is partially already playing a role, but will have a more prominent role in future.
Okay, thank you. Then the next question to Judith. Given the design life of floating offshore wind assets will be 20+ years, has Dyneema considered the long-term integrity management of mooring array monitoring, risk-based inspections? And the follow-up question is that great presentations. Are there interesting technologies? Are they proven and certified?
Okay, can you repeat once more the first question?
Yes. Given the design life of floating offshore wind assets will be 20+ years, has Dyneema considered the long-term integrity management of mooring arrays, such as monitoring, risk-based inspections, and such? And the follow-up question is that those technologies are interesting that you discussed, and are they proven and certified? Indeed. So 25 years, of course, is a long lifetime. We looked really into the main failure mechanisms, and the advantage that we have as a fiber supplier is that we, as I indicated, we are backwards integrated, so we make our own raw material. That means that we can tweak on a molecular level, and that is what we did with the fiber, which is called DM20. That we really tweaked in order to give that the longevity. In many of those applications, fatigue is the main failure mechanism, and that functions different than with steel. So it is not so much the tension and the amplitude, but it is really about the main loads. We are 3T dependent, so on the time, temperature, and tension. And in order, we built models to predict that behavior. These models are DNV qualified. So that means that we are able to use that. And in many of those cases, we are allowed to use a safety factor of 3 on those calculations. It means that we need to predict for 75 years, but that can only be done if the input value is reliable. And of course, to get reliable inputs, you need to do good mooring designing, and that is why we also developed models in order to do more accurate mooring analysis.
Of course, yeah, maintenance, we don't corrode. However, as indicated, yeah, also this fouling needs to be monitored. And because it adds weight to the complete mooring system. And that is, yeah, something that needs to be monitored. On the other hand, we are doing studies also on yeah, different locations to monitor the fouling. And to answer to the second one, so if we look to the different projects where Dyneema is currently involved, that is the wind float Atlantic, that was EBS certified. It is now installed for 4 years. Also the Kinkerdine was ABS. The Stiesdal, which is approaching its 2-year anniversary milestone, there it was according to DMV. It is not, yeah, DMV aligned standards. And then the next one, which is going to be installed soon, is the Golfe de Lion. That will be with Bureau Veritas. I hope that answers the questions.
Okay, great. Thank you very much. And next question is to Olli. So, based on your experience and expertise for the general offshore wind industry, would you say that it's more beneficial to start a new port and plan everything from the scratch, or adapt transport and installation and maybe fuel strategies to the current ports available from the technological point of view? Let's say, I don't know, for the UK or Asia, Singapore, if you can say something.
So yeah, this would be pretty much more southwest based, and I think there's been various studies looking at ports around the southwest, and I think primarily ports are set up because they have natural advantages, and that's why ports have existed there in the past. So I think it's pretty much, I think you have to use the infrastructure you have unless you're doing huge amounts of sort of civils to reclaim land, and there is opportunities there, but I think it will be primarily in changing ports that already exist and adapting them to suit the offshore wind sector.
Okay, great. Thank you very much. I think we have time for just one last question and very short answers. Which trends do we foresee in the next 10 years regarding the technological developments in the offshore wind industry? Maybe we start with Olli and then Judith. Last, just 30 seconds.
Well, I think there's going to be a huge amount because especially floating offshore wind in the next 10 years, it's going to be completely different from where we are now. There's going to be a huge amount sort of in there and offshore. And I think there's going to be massive developments in the shipping industry as well. You're going to see much more sort of e-fuels and different vessels operating and working on these offshore sites than we have now.
Okay, great. Thank you. Judith?
Yeah, the same as Olli mentioned. Yeah, I think the scaling up, the standardization, but also together with the question which was raised about sustainability and recycling, that will get more and more attention in the coming years. So yeah, enough challenges to cope with, but I think it is interesting challenges that there are enough innovative players that are willing to accept those challenges.
Okay, great. Thank you very much. That brings us to the end of this webinar, unfortunately. It would be great if you can join us next month, in June 20th, and the next topic will be offshore wind development challenges. And as for today, thank you very much, Judith and Olli, for your presentations today, and the audience for attending this webinar. The webinar has been recorded and will be uploaded to our YouTube channel. If you'd like to share it or watch it again, please feel free to check out our YouTube channel. So have a great rest of the day, everyone, and see you next time.
Thank you.
Thanks very much.
Bye.